Welcome to EE380, Stanford Colloquial on Computer Systems, Spring 2018-2019. I'm Andy Freeman. The other course organizer is Dennis Allison. Seeing is believing. That's not quite right. Seeing is understanding. While images have relatively little information content, compare the number of bytes you need to describe the slide up there with the number of bytes you need to describe it as an image. Images let us, humans, see and understand things that we wouldn't do as effectively if it was text or some other form. Simulations are another powerful tool to help us understand systems and processes. They let us try alternatives, run things at faster or slower than normal speed, and otherwise replay the world. Today's talk is about using virtual simulation visualize simulation to effectively wargame physical infrastructure. The goal is to understand threats, consequences, and the effects of various responses.
Thank you, Andy. And thanks all of you for coming here. I can see some friendly faces in the audience from way back in undergrad, so it's great to be here. And some of you are related to Singapore in one way or the other, so you might find this talk relevant in more ways than just the content of this talk. So this talk is about virtual reality in cyber-physical systems and how it leads to smarter cities. So my lab basically works on security, and I'll just tell you in a bit how we started working on this field altogether. So I'm Sid, and I'm a researcher at iTrust. So iTrust is the Center for Research in Cybersecurity, and it's the leading cybersecurity center in Singapore. It's located in this very unique university called the Singapore University of Technology and Design. So this was set up by MIT in collaboration with the Singapore government to set up a multidisciplinary, unconventional curriculum. So we don't have fields like computer science or mechanical engineering or humanities. So there are pillars instead. So one of them is the engineering product development pillar. So every undergrad has to learn fabrication, designing, and they need to learn how to program things in the real life as well as in the digital life. So it's a very unique university in that sense, and it's been there for 10 years now, and my lab has been there for around 6 of those years. So I'm advised by Professor Aditya Mathur, who is the director of iTrust, and he also happens to be the head of computer science at Purdue University. So he was the person who was most excited when I told him about this talk, because he collaborated with Professor Donald Knuth on some review paper in the 1980s. So his experience goes way back. He started the first computer science department in India. So he's highly revered in the field of computer science. So right now he's the director of this lab, and with him I work on fields like virtual reality, computer science, any field of computer science. So we mostly do distributed systems and game design and formal methods. So all of these things to contribute to security. So I graduated from this university in India, there are familiar faces here who graduated from the same place. Then I worked at the Indian Space Research Organization and collaborated with the MIT Media Lab. I spent 2 years at an investment bank, as you can see, and then I made the jump to this lab where I work at now. So my first introduction to virtual reality and teleoperation was in this Google Summer of Code project, in which I had to build a teleoperation system for humans who go to Mars in the future. So this was in collaboration with the European Space Agency. So the idea was that the astronauts are safe inside a habitat and they have to control the rover outside. So the astronaut walks on an omnidirectional treadmill by wearing a VR headset, and whatever they see, the rover sees, like whatever the rover sees, they see, and whichever way they move, the rover has to move the same way. So basically the astronaut is an extension of the rover that's moving outside. This was primarily because it's not safe for humans to go outside into the Martian environment, even when we have fully developed suits and everything. So that was Oculus Rift Development Kit 1, which was one of the first headsets that came out for virtual reality. And it was very painful to get anything working on that if you have worked on that. So what I want to show you today is how far this technology has come in just 3 years and how far it is supposed to go. So first I'll tell you why Singapore even cares about security or virtual reality so much. So in the defense budget, they allocate 30% of the budget to cybersecurity, this is an update from 3 months back, so it's a relatively new thing. So the defense is focused on these different pillars. One of them is military, then social defense, in which we have social security for the citizens, then civil defense, in which all citizens have to go through, all the men have to go through national service at the age of 18. Then economic defense, like all the economic safeguards that are there to protect Singapore. Then psychological, and the latest pillar that they added, which is digital defense, which includes all the cybersecurity and cyber-physical systems research that we do. So recently my lab got funded in 7 figures to make Singapore the primary hub for cybersecurity research. So that's why this talk is based on that. One more thing, like Singapore opened the world's first virtual reality theme park, which like just a few months back. So even though virtual reality was pioneered in this country, it is being commercialized in Asia more. So this is a Korean theme park which opened in Singapore very recently, and they have levels for different kinds of people depending on their skill level in virtual reality. So if you have motion sickness, you can use easier rides, VR rides, and they have things like harnesses and stuff to make you as immersive as possible. So the title had this term cyber-physical system in it, which might be new to some of us. So I'll just basically focus on what it means. So we start with cyber-physical system is anything with a sensor and an actuator, which is controlled by a computer. So everything is a cyber-physical system, from the lights in this room to your mobile phones to smart cars to your power grids of your cities. Everything is a cyber-physical system. So it's called cyber-physical because it has both cyber components and physical components, and both can be controlled via the other. So you can control your physical components through the cyber medium, and you can impact cyber things through the physical medium. So this is a very formal definition of cyber-physical system. So I'll just spice things up a bit, and for the young people in this room who grew up watching Iron Man, that is a very excellent example of cyber-physical system. And I'll use this example to show the different kinds of attacks that are possible in a cyber-physical system. So cybersecurity in the traditional sense only had cyber attacks in which your computer was infected with a virus, and then it slowed down the computer or it snooped on your files or something. But when you add a physical dimension to it, the class of attacks just widens much further. So you have all these 4 possibilities in which you do a cyber attack which has a physical consequence. You have a cyber attack which does only a cyber consequence. You have a physical attack which has a cyber effect, and a physical attack which just has a physical effect. So without spoiling anything from the latest movie, so this is one of the kinds of physical cyber attacks. So let's say your smart car meets with an accident. So that somehow damages the onboard computer. So that's a kind of a physical cyber attack, because a physical impact on your system impacted the cyber processes of the system. So this can have both a cyber and physical impact. What my lab mainly focuses on is a cyber physical attack, in which you hack, which is the traditional way in which we know cyber physical attacks. You hack into some system, you get access to it, then you control the physical components. So if you remember this scene from Iron Man 2, so the hacker just got into the Iron Soldier and controlled a whole fleet of these suits to like just wreak havoc on the city. So this is not just a science fiction example. This actually happened. In 2016, the power grid of Ukraine was controlled by hackers, and they got the city down for two whole days in the middle of the winter. So that is a big thing which is happening these days, and that's why we need ways to detect these attacks and avoid such attacks. So the domain which I'll be focusing on today is a water treatment plant, and I'll explain why very soon. So to establish the correlation between a cyber physical system and a water treatment plant, so all your manufacturing plants, nuclear plants, these are all cyber physical systems which are called critical infrastructures because they control, they have a very huge impact on the economy of a country. So everything, all these plants have one thing in common. They have a very similar architecture. So you see a historian database in which all the plant operations get stored, like what's the level of the water right now, and like everything gets stored in a centralized database. Then you have programmable logic controllers in which there are algorithms which decide what to do in a particular process. So for example, the pump should turn on if the water level is low. So this is a very sequential programming, this is a sequential style of programming called ladder logic, in which every step has to happen in sequence. So these things control sensors and actuators. So they get the data from the sensors, they estimate the state of the plant, then they control the processes using the actuators. So the architecture is somewhat like this. You have a physical process which is estimated by the sensor. Then the PLC reads the sensor readings, then the PLC tells the actuator what to do, and it impacts the physical process. So the good thing about these PLCs is that they're localized to the stage in which they operate. So if you have 6 stages, let's say ultrafiltration, dechlorination, and all these different stages in a water plant, every stage will have its own local computer deciding its own local actions. All of these computers are connected to a centralized computer called the Supervisory Control and Data Acquisition Unit, or the SCADA system. So these blue stars indicate that all of these points are prone to attack. So what we did at the lab is we put defense mechanisms at each of these points. And one of the things I'll be demonstrating is how to visualize defense and how to visualize attacks. So for example, these are the electrical wires that go from the sensors to the PLC. So we went a step ahead of all the things that are out in the industry, and we captured the electrical current and voltage signals, and we assumed that a hacker cannot get to the electrical and voltage signals part because they typically focus on the network part. They get in through the network. So we capture data from all these different levels, and we have the most accurate state of the plant. So even if this stage is attacked, we have the lower stages to tell us what the actual value of that plant is. By an attack, I mean if the tank is 80% full, the attacker can report it's just 20% full, and that will just mess up with the programming of the entire plant. That will tell the pump that it should turn on, and the tank is actually 80% full, so it will turn on thinking it's 20% full, and the tank will overflow, and you know what will happen next. So what enables us to do all of this stuff is that we have a hackable testbed. So our water treatment plant is as big as this room, and you can see that we have access to each of the connections in this room. So I've just placed a Raspberry Pi as a small project that we were doing. And that's not the only testbed that we have in the plant. So this makes our lab the only place in the world in which you have a water treatment testbed, a water distribution testbed, an Internet of Things testbed, and a power grid. The good thing about it is that all these are connected. So this means that you can study cascading effects of attacks on one particular testbed and see its effects on another testbed. So let's say you had a smart home device in your Internet of Things lab which had a vulnerability which the hacker got into. So they somehow got into the lab network, then they moved to the power grid. They attacked something in the power grid which affected water treatment in some way. So since the water treatment did not get power, which it wanted to get to operate properly, this impacted the water distribution in the city. So it's a cascading effect which we can study in an environment like this. So I'm just coming from Kansas City in the Department of Homeland Security's conference on industrial control systems. So they are trying to build a similar setup for all 16 critical infrastructure sectors. And like Japan seems to be doing the same thing. So like we did this about 6 years back. So we have a lot of collaborations around the world, and some of the best time series data sets that you can get for real physical processes, which many people have requested for, and they use it for testing their control systems methods or formal methods or computer science methods to detect attacks. So this is just a quick tour of the lab. So this is one of the stages. Then you go to the raw water stage. So you can see these are the programmable logic controllers. They are always redundant. Then we have installed different projects at different stages. So you have 6 stages in a room as big as this, and this is just one of the test beds of the 4 that I showed you. And I'll be giving you a closer look very soon. So I want to tell you how the world interacts with this. So you see the screen. The operator just operates it using a traditional mouse and keyboard or touch screen. And the thing about these interfaces is that they are hard coded by the vendor, and they are frozen at the release time of the plant. So they do not have any way to visualize attacks on the system or if something is under attack or any defense mechanisms of the system. All they tell you is the value that the database is seeing. So if that value is corrupted or hacked, then you have no way of telling what state the plant is under. So what hackers typically do is they get remote desktop access to this particular interface, and that's how they usually attack the plant. So how they achieve that is they send a phishing email to the operator, or they infect their thumb drives with some virus, which is how the Stuxnet attack also happened, if people in this room are aware of that. So now I'll just show you a quick demo. So what I have here is an Oculus Rift headset. So my position will be tracked by these 2 sensors here, and I'll have all the degrees of freedom for my hand using these touch controllers. So you will be seeing a very narrow view of what I will be seeing. So I urge you to try out the demo, because virtual reality is in 360 degrees and 3D, and what you are seeing is a 2D screen with a very narrow field of view. So you won't be appreciating it as you would when you try this headset out. So I'll just start the demo now. Now, because of the space limitation, it's not calibrated as well, but it should work.
Hi, welcome to iTrust. Our research focuses on the development of advanced tools and methodologies to ensure the security and safety of current and future systems in 5 key areas: cyber-physical systems, or CPS, Internet of Things, or IoT systems, enterprise.
Just a second.
Hi, welcome to iTrust. Our research focuses on the development of advanced tools and methodologies to ensure the security and safety of current and future systems in 5 key areas: cyber-physical systems or CPS, Internet of Things or IoT systems, enterprise networks, autonomous vehicles, and blockchain.
So yeah, this is a digital tour of my lab, and this was just an introduction. I'll walk you through my lab. So you see my hands here, and you see that I can make all kinds of gestures here for different actions. So let's just walk through the lab.
We have the following test beds for representing different critical infrastructures: SWaT, Secure Water Treatment Testbed; WADI, Water Distribution; and EPIC, Electric Power and Intelligent Control. I'm Aditya, and I'll guide you through this entire journey. Follow the blue arrow and complete the objective to move on to the next stage of the tutorial.
So
Let's start with the different interactions you can perform with your controllers. Follow the signs to complete the objectives.
So this is just a place where people who use VR for the first time, they can just play and see that we can modify physics as we want. So in this case, we don't have gravity as soon as you touch the ball. So this is just a place to familiarize the person with the virtual reality environment.
Great job! Now let's show you what SWaT looks like. All of these components combine to accomplish individual tasks and hence divided into stages. Take a good look at them.
So you have all kinds of freedom. So I can move around if I had more space, and you will move around in the VR environment as well. I can squat if I want to, and you can focus on particular components. So these are all the different sensors and actuators we use in the lab. So the ultraviolet module and the pressure indicator.
P1 supply and storage.
These are the
P2
stages.
pre-treatment. P3 ultrafiltration and backwash. P4 dechlorination system. P5 reverse osmosis or RO. P6 RO permeate transfer, UF backwash and cleaning.
So that's the network architecture of the lab.
Now SWaT consists of a modern 6-stage process. The process begins by taking in raw water, adding necessary chemicals to it, filtering it via an ultrafiltration or UF system, dechlorinating it using ultraviolet UV lamps, and then feeding it to a reverse osmosis or RO system. A backwash process cleans the membranes in UF using the water produced by RO. The cyber portion of SWaT consists of a layered communications network, programmable logic controllers or PLCs, human-machine interfaces or HMIs, supervisory control and data acquisition or SCADA workstation, and a historian. Data from sensors is available to the SCADA workstation and is recorded at the historian for subsequent analysis. Let's get you familiarized with the monitoring screens. Click on the text on the green screen using your hand, mouse or your laser pointer to obtain values for the components.
So this is just to show that you can work with a virtual environment in the same way as a real environment. So you would have touchscreen panels in the lab, and you can do the same things here. So this enables a lot of applications such as remote teleoperation. You don't even need to be in the lab to work on the lab, and that's what we'll see in this demo.
Look around you and enter the simulated SWaT by the door.
So if you visit my lab in Singapore, this is part of what you will see. So
The
that's
space is where the SCADA and historian is managed from. Now let's go take a look inside SWaT, through the glass door if you may,
so
and
this is
proceed to the area
this is the
marked
interface
with
that I
the arrow.
showed you before. So these
In
are the
stage
same
1,
stages.
called the raw water processing stage, raw water is stored in tank T101. Water comes into tank T101 through the motorized valve behind the tank. Water flows out of this tank to stage 2 through the constant speed pump here below.
This one.
These two AIT indicators indicate the pH level and the oxidation reduction potential, or ORP, of the raw water. In stage 2, called the chemical dosing or pre-treatment stage, appropriate levels of 3 chemicals are added to the raw water: hydrochloric acid, HCl, sodium chloride, NaCl, and sodium hypochlorite, NaOCl,
So
for
I'll just
disinfection
skip this
and
part because
pH
it's
and
very
ORP balancing
plant specific.
of the raw
So
water.
if you are in the water industry,
These are dual dosing
you can
pumps to control the
contact
flow
me
of
later.
the chemicals.
I'll just focus on the generic
This is stage 3, the ultrafiltration stage. This pump here will move the water from tank T301 through this UF or ultrafiltration unit to the tank T401. The UF unit contains micrometer membranes to remove solid matter from incoming water. This stage contains a number of motorized valves.
Yeah, so one of the things that virtual reality offers us is that we can redesign the environment as we want. So it doesn't have to be a cluttered lab layout like you just saw. So what we did was we laid out the lab again by redesigning it in a very accessible fashion. So this is stage 4, stage 5, stage 6, and back to stage 1. So this helps us in visualizing a lot of things, which I will just show you. So you get more context about the plant because you can add as many assets that you want. So I'll just show you one of the applications that we developed. So instead of after a cyber attack happens, the operator has to go through the database logs and figure out what went wrong at what step. So that is a very tedious process. So what we did was we made that process visual. So you can see the plant breathing, you can see the plant moving up and down at a speed which is not natural for the plant. So water is a very slow process, like water moves up and down very slowly. So if we speed that process up, we can see how the plant is behaving, like at what point the pump turned on, at what point which valve closed. So I'll just open an 11-day data set. So this is an 11-day data set that I'll just play at a very fast speed. So you can visualize 11 days in a few minutes. So 7 of those 11 days were normal operation and 4 days were attacks. So we can see both the cases when the plant starts reading the data set. So anytime now it will just start. So yeah, you can see the plant breathing. So if there's an attack, it will show it as an attack, and if there's a particular component which is attacked, it will turn red. And you can see the plant moving, you can see the different parts like the pumps. Like if these things are green, that means the pumps are pumping water to it, and that's why the levels might be increasing or decreasing in a particular stage. So you see all these values changing, which are the different sensor values. You can interact with the touchscreen panels in the same way you would do in a real plant. So the reason you see two values here is the same architecture that I showed you earlier. So PLC is the reflected value of the plant, which may be hacked. We developed a project called IC, or Intelligent Checkers, which is the thing that I told you, in which we distribute our detection mechanism across the plant, and we measure all the values to see what's the actual value of each component in the plant. So So you can see the level, LIT means the level sensor, and you can see that both these levels are the same. You can see the water going up and down, and if it's a critical attack, you can alert the plant operator accordingly. And if you want to slow down the rate of this data transfer, because water doesn't really move up and down this fast, you can do that. So I'll just show you that. So if you look at the time lapse rate, it says fastest. So now I'll slow it down a bit. So now you see that it takes 0.3 seconds for every step of the data set. So now you see it move very, very slowly, which is closer to the real situation in the plant. So in case there is an attack, you can freeze and analyze the situation of the plant and see what went wrong, which part was attacked by the attacker first, and you can do all those kinds of analysis, which is important for recon. So we did not stop at this. We further redesigned the plant, and we added a heads-up display, which you see very partially here. So what I'm seeing is something closer to this. So you see all these different components, and now I have a laser pointer instead of my hands, and you can see my controllers. So you have a map, mini map here, which shows you the location of your character in the plant. So this is a small plant, but when we extend this to a real world plant, when these are huge plants across multiple rooms, so you need to know what went wrong where. So you can teleport to any particular stage in the plant just by focusing on it. So I just clicked on stage 4 and I was teleported to stage 4. So stage 6. So if there's an attack here, you can just go directly to that stage and see what's wrong in that particular stage. Then we have different detection mechanisms. So this might be of interest to people here because it's physics based. So invariants are physical conditions which must be true. So the idea of this detection mechanism is that the attacker can fool the plant in whatever way they want, but they cannot fool the physics of the system. They cannot make water go at a rate that's more than what gravity allows it to go. So we have these conditions that we derived both using formal methods as well as machine learning. So that's another project that I want to visualize through this virtual reality environment. So what this says is if the motorized valve is open, then the water flow in the flow indicator should be more than 0.5. So if it's not violated, it turns red. And that's what this is trying to show. So we can also see a summary of the different things happening in the plant. Like it's just an easier way to access what's happening at each of those stages. So the pump 101 is on, which is true. You can see it's green. And the pump 102, which is behind it, is off, which you can see it's not green, so that's why it says 1, which is the code for off. Now I'll try to connect to my lab's VPN, and if it connects successfully, we can access the plant live through a virtual reality environment. And I'll invite one of my lab members to show you around the lab. So usually usually how this demo goes is I connect my lab through the VPN, and then we do attacks here, which you can visualize here. Someone does an attack there, which you can visualize in this environment. So Salima is a researcher at the lab with me, and it's, I guess, 7:30 a.m. in Singapore. So she'll just walk you through SWaT. So can you go inside SWaT? So she's in the control room right now. Yeah, go inside. So she's in the room next to the testbed. So she'll just show you the different parts of the testbed, and she'll do a live attack there. So she has developed an attack tool in which we work with vendors to attack the plant in whatever way we want, like man-in-the-middle attacks or network-based attacks or physical layer attacks. So we use the virtual reality bit to demonstrate and visualize those attacks. So what you see here is stage 6. So Salima can change, so you can see the value in stage 1. Can you focus on stage 1? Yeah. LIT 101. You can see that, the water level. Like I want to show them the water level. So you can see it's close to 1100 right now. And now she can change it to some other value using the interface that I showed you. So Salima, can you modify it to 200?
All right. Let me go back to the main room.
You can do it from the touch screen, right?
Sorry, what?
You can do it from the touch screen there. Okay, it's open, so no problem. So just focus on the monitor.
Can you see it?
So you can see it says 600. It says around 1100, and she can modify it to be 200. So this is how this is one way how the plants are attacked. So there's a disgruntled employee or an insider. They just want to mess with the plant. They still have their credentials after they are fired, so they can just remote desktop access to it, and they can modify it as they want. We can also do network-based attacks, like using Python scripts. So what she's trying to do is, she's made it 200, I think, and
not yet. I can't change it because the other tank is high. So I'll change tank 3 to 200. Is that okay?
Yeah, okay. And can you launch an attack from your computer using PyCom?
PyCom now, I have to set it up because I need Wi-Fi. Yeah.
Okay, no problem. So, like if the VPN was working, you would have seen this environment, see the same values, and you can see what thing is being attacked at what point. And you can do an attack here, which she can show there, and vice versa. So the idea is that a technology like this enables teleoperation. So maybe your factory doesn't have skilled workers to work on the 30-year-old PLC that you have. So you can just outsource it to some other country's skilled labor who can guide you through the virtual reality environment, and they can guide the lesser skilled person in their country to modify the plant, because VR enables you to spatially move around and like interact with things. So things which require you to turn, rotate, and work with objects in the 3D space, virtual reality helps you do that. So you can easily do that with just a network connection. So okay, while she sets it up, I'll continue with the rest of the presentation. So this is also being used by the water companies in Singapore. So we are working with the main water company and soon power companies of Singapore for training purposes as well. So this is used to show the new employees how the plant works, and you can give them short quizzes while they are walking through the plant to get how much of the plant they know. So the US Navy already uses such a system for training their new recruits on submarines even before they enter the submarine. So you can just answer all these questions and see how much you have grasped about the plant. So you can use this for training purposes, which is one of the main applications of VR these days. So all the companies use it commercially for training purposes. And now I'll continue with the rest of the presentation. There is another demo soon on another topic, so stay tuned for that. So this project got, it's just a 7-month-old project with just 3 undergrad students, the professor and me. So this has got a lot of recognition since then. It got an award by the equivalent of Y Combinator in Singapore. So this is a startup accelerator which found this project worthy enough for an award. We had the US Navy head of research visit our lab to see the different technologies that we have built at the lab. So you can see my lab director showing it to the US Navy head of research. Then this was one of the highest profile visits that we got that happened during one of the summits in Singapore. So the president of Chile visited our lab, and he actually wore the headset and conducted live attacks on the plant. So that was a pretty big thing for us. And I've been on a mini talk tour, and I gave this talk first at Kansas City just 3 weeks back to the Department of Homeland Security, which is the reason I am in US right now. So this is just the beginning. What we want to actually do with this technology is we want to visualize interconnected infrastructures. So we want to see the different layers that drive a city. We want to see the city level impact of different power grids and nuclear grids and your transport grids and how they affect each other. So we want to study cascading effects, and we want to develop it into a sort of a serious game which is accessible for policymakers like presidents and the heads of states, so that they can revise their security policies. So what we did is we took one of the tools developed by the Environmental Protection Agency here called EPANET. So what EPANET does is it can help you simulate water distribution networks very well. So it's a simulator. And what my lab did is they added a cyber physical attack portion to it, so you can have digital components and you can affect the distribution in various ways. So this also got the best paper award at the top US conference very recently. So we connected this simulator to our virtual reality, to one of the mini games that we developed. So I'll just show you that. So I can show it to you through my Oculus Rift, and there's a video as well. So what you see is a city, and with just a click of the button you can see the water grid portion of that city. So you can see how the city functions, like which tanks are being operated at what time, which pumps are on, and you can see the correlation between the tank and the city in the city's water grids. So this is one of the attack scenarios that we have. So there's a distributed denial of service attack. An attacker has affected multiple PLCs. So you have to go and stop the attack as the person who manages security in the city. So first you will focus on the water layer because that's where the attack has happened first. So your physical component has been affected. So you have to go and manually check that. Then because it's originating from a cyber point in the city, so you have to trace the attacker and see at which point that attacker is in the city. So you see that the cyber attack is coming from somewhere there in the city. So you try to go to that physical location, trace the attacker down. So you stop the distributed denial of service attack, and now we will see the negative demonstration in which we are unable to stop the attack, and we'll see the consequences of that. So now this is a realistic scenario because the speed at which these attacks happen, it's mostly too late to do anything about that. So we are unable to guess what's happening. So we're just trying to see where the attacker is and failing at it. So you see the similarity between the tank in the city and the water grid. And because we are unable to stop the attack, it's overflowing the tank, as you can see. And just with a simple cyber attack, the attacker is able to overflow the tank. And one of the consequences could be this. So the point of this talk is this is not a fictional scenario. Because it has happened on power grids and transport grids, it can happen to any of the critical infrastructures and nuclear grids in the case of Stuxnet. So it can affect any of the infrastructures. So because this talk had a mixed reality component to it as well, so the next phase of the project is to use a headset like HoloLens and develop something like the demo that they just showed 2 months back. So this is an augmented mixed reality headset they released very recently.
Which includes live IoT data streaming in from an actual blower out in the field. While this experience offers significant benefits from a time and cost of training perspective, thus far it's only been geared for individual participation. But now, let's make it more collaborative. By leveraging the Azure Spatial Anchor service within Vuforia Studio and View, we can let Maria seamlessly join in Alex's experience. Maria can simply take out her iPad and launch Vuforia View. Once Maria points her iPad at the same location where Alex placed the blower, she can participate in the mixed reality experience, making it far more interactive and collaborative.
That's right, Jim. Now that Alex and I can share the same experience, I can create a number of different training scenarios. Alex, let's simulate a gear failure mode.
Uh-oh, I see their gear vibration went down, and I have here threshold exceeded. Please inspect. Let's go ahead and select that.
Alex, I think you might be dealing with a broken gear tooth. And you will probably have to replace the gear assembly.
All right, I'll roll up my sleeves and get some work done here. Let's do it. I'm ready.
Right, I'm going to start the disassembly instructions for the gear assembly.
So these people don't have to be in the same physical location. They can be in geographically different places.
Now that Alex is using HoloLens 2, he has access to a wide range of hand and eye tracking capabilities that are all available in Vuforia Studio and View.
All right, let's put it back.
That is so awesome.
Fantastic.
Vuforia Studio.
So as we get more and more sensors in our plants, we can develop applications like these and use it for asset maintenance and see which of the parts of the plant have degraded in quality over their lifetime and replace them right from your virtual reality environment. So before I summarize the talk, I'll just walk you through the lab again to see if So we saw that it can be used for, such an environment can be used for simulation training for operation and maintenance staff. You can walk them through the plant even before the plant is built and train them on different scenarios in the plant. You can have a very distraction-free interface. So what typically happens in these plants is you have 20 screens and the operator always misses the true positive signal when an attack is happening. So because of such information overload, it is important to design better interfaces which have a very focused view on which attack is happening at what point, or which malfunction is happening at which component. So, and a VR environment forces you to be in a very distraction-free environment. You cannot really look in the real world unless you want to. So, unless you remove the headset. So once these headsets get comfortable, it can be a replacement for monitor-based interfaces. Then you can visualize abnormal operation and cyber attacks like floods and explosions. So I did not show you that part yet. I'll just show you. So this is one of the, so in case an attack happens, so your environment can tell you it's about to flood even before it's flooding. And if you think this is a fictional scenario, we have flooded our own lab on 2 occasions. So we know that it's very much possible, and that's why it's a test bed, and we can afford to make these mistakes, but you cannot do this in a government-owned water plant or nuclear grid. So that's why we need better security techniques to detect these attacks, and which is why the research and these visualization tools come into picture. So we saw that we can visualize defense mechanisms. So we can see which parts of the plant are being attacked. We can see the direction that the attack is flowing in. We can understand the attacker's intentions. So an attacker is usually very smart. So they do not just do a full-blown attack right on getting the access to the testbed. So even in the case of Stuxnet, they waited for a long time, in the order of months, to understand the whole plant. So they used to just do small, slight modifications which went unnoticed by the plant operators. So they understood and did a full recon on the plant for more than a few months. So before they launched the full-blown attack, in which they stopped the centrifuge, which affected the manufacturing in that nuclear plant. So understanding the attacker's intentions is very important. So they might start an attack from a pump, but that does not mean the pump was their main focus. They might be affecting some other component in some other stage. So using a visualization tool in which you can see cyber attacks, you can see the direction that an attack flows in, and you can gauge the intentions of that attacker even before the attack happens. And this is one of the things that I am most excited about. So with the help of VR, people in Stanford or anywhere in the world, they can collaborate with us on our test beds. They can conduct experiments, or whatever kind of experiments. They can test their defense mechanisms. They can move around the plant, conduct attacks, and collect data from the plant. So this enables you to do it remotely, and you don't have to fly to Singapore all the way to do this. So virtual reality as a remote collaboration tool is very promising. So that's why one of the demos that I wanted to show with the VPN working was to connect you to the lab and see the two-way relation, that this is an extension of the real lab and the lab is an extension of the virtual world. So that is asset maintenance was the mixed reality demo that I showed you, and we can use this as a city manager to visualize interconnected infrastructures. So you can see the water layer of the city, the power layer, and you can see what kinds of attacks at what layer might affect the city. So interconnected infrastructure is going to be a very important topic for smart cities. So this virtual reality and mixed reality technologies can come in handy big time there. So thank you for taking the time to come out to this colloquium, and it's been a privilege to speak here and go around the states and talk about this research. So I'm here in San Francisco for about a week more, and I'll be returning to my lab after that. So if you want to connect with me, just reach out to me after the talk or connect via LinkedIn. You can just point your phone to the QR code. It will take you there. So thank you. So any questions or comments? That's the end of the talk.